Alright, you guys. So in the previous one we talked about exponentials, and as you can see from the notes, it's still the same page. In this one, I'm going to talk about logarithms. And the reason these two lectures are combined is because these two types of functions are very similar, and they're actually kind of related. If you guys remember when we talked about inverse functions, a logarithmic function and exponential function are actually inverses of each other. But I'm going to get to explaining that later on. For now, let's introduce the logarithmic function and see what it actually means. Okay? So, for a log function, let me write the definition for you real quick. It says, if x and b are positive real numbers. If you want to write this in your notes, go ahead, but you don't have to. It's already in my notes. It's at the very beginning, the definition. Very top of the first page. Okay, so anyway, so if x and b are positive real numbers, such that b itself does not equal 1, okay, then y equals log base b of x is called a logarithmic function with base b. Now, where, and please note this part, y equals log base b of x is equivalent, let me move this a little so I can have room to write, equivalent to, I'm going to write what is equivalent to right here, b to the y power equals x. These two are the same thing. Notice one is in exponential form and the other one is in log form. Alright? So, when you see a logarithmic function, it's going to look like this. Y, your function, log of x. So, the log that you are taking is of x, the number right next to it. The b that you see over here is the base of the log. You usually write this in smaller handwriting, smaller size, and it's glued to the bottom of the g over here. Okay? So this is not a number you're multiplying by the x. This is not a number you're dividing by. This is the base of the log, and it's always attached to the log. Alright? So the base of the log is going to be the same base you use when you have an exponential function. These two. Same base. Now, this is the answer of the log. This is the value inside the log, and this is the base of the log. Right? Let's play with it a little. I'm going to give you a few log forms, and I want you to write it in exponential form. We're going to do this together. Here we go. First example. Let's say we have log base 4 of 16 and it equals 2. Now I want to write this in exponential form. Okay? Now, notice the difference between these two. The base of the log is the base of exponential form. The base of my log over here is what? 4, right? So when I convert to exponential form, it's going to be over here. The exponential form has b to the power of y, which is right here. So the answer of whatever the log is, y is the power. Okay, so whenever you're finding a log of a value to a certain base, the answer is actually the power. Alright? So, y over here. So since the answer to this log is 2, it's 4 to the power of 2. And it equals x, which is the value you had inside the log. Which is, in this case, 16. Now, to make sure you did it right, does this right here make sense? When you square 4, or you multiply 4 by itself, do you get 16? The answer is yes. Alright? So as you can see from here, this is the relation between an exponential function and a logarithmic function. Let me give you another example. How about log base 5 of 0.2? Okay? And it equals -1. Now let's write this in exponential form. Now, the base of the exponential form is the same as the base of the log. b, right? So, what's my base over here? It's 5. So it's going to be the base 5. The power is the answer of the log. So it's -1. 5 to the power of -1. Which equals what's inside the log, which is 0.2. Does this make sense? Now this is a little harder to see, but yes, it does. Because you see, when you have 5 to the -1 power, like we saw in the previous section, what happens? This becomes 1 over 5, right? 5 in the denominator. And 1/5 actually does equal 0.2. Make sense? So this is also true. Okay. How about this one? Log to the base of 8. So this is the base of your log. Now what's inside the log is the number 1. And it equals 0. So let's write this in exponential form. My base is still 8. The power is the answer of the log. So it's 0. And the answer is what's inside the log, which is 1. Does this make sense? The answer is yes. Anything to the power of 0 is always going to be 1. Which should give you a hint. Whenever you're taking a log of the number 1, no matter the base, the answer is always going to be 0. But I'm going to write that property down for you to have in your notes later. Okay? We're going to discuss it more clearly a little bit later on. Anyway, so here's another example. Log to the base of 23. Inside the log we have 1. The answer is 0. Can you guys do this one on your own? I'm going to pause for a few seconds so you can stop the video if you want. Now, first thing we start off with is the base. What's my base here? It's 23. Okay, 23 to the power of what? It's 23 to the power of the answer of the log, which is 0. And it equals what? It equals what's inside the log, which is 1. Now, having practiced it a little bit, let me rewrite the relation between a log and exponential function so it's easier to remember. Okay? So let's say this is your base, P is your power, and A is the answer. This is my exponential function, right? This is the exponential form. Now I'm going to write the log form. It's going to be log base B, again. If it's the base of the log, it's going to be the base of exponential function. Okay? The inside of the log is going to be A, the answer, and it equals P, which is the power. The reason I changed the letters is because it makes it easier to remember. The power is the answer of the log. The answer of the exponential function is what's inside the log. Now you can memorize it this way, or you can memorize it this way. So these two lead to each other. Okay? Whichever one you find easier. Either this one or that one. Okay. Now we'll do it in reverse. Okay, you guys? I'm going to give you a few examples of exponential form, and we're going to write them in log form. Okay? Here we go. How about 2 to the power of 4 equals 16. Now I want to write this in log form. Okay, so the base of the exponential is going to be the base of the log, right? So log base 2. Correct? Now what's inside the log is going to be the answer of the exponential. So over here goes the 16. And the answer of the log is going to be the power, which is the 4. Yeah? Let's do another example. How about this one? 27 to the 1/3 power. See, I'm starting to get a little mean here. And equals 3. But don't worry, I'm not asking you to solve it, just convert to log form. So, here you go. Log, the base of the exponential is going to be the base of the log. So it's base of 27. Now, the answer of the exponential is going to be inside the log. So it's log of 3 base 27. And the answer of the log itself is going to be the power of the exponential, which equals 1/3. Okay? One more. How about this one? You have 1/4 to the -2 power, which equals 16. Okay? So, if I wanna convert this to log form, here we go. Log base what? What's my base? It's the 1/4. So 1/4 goes on the bottom. Again, your base is the value that has a power. So since the 1/4 is the one with the power, then the 1/4 is your base. Make sense? So I'm writing the 1/4 at the bottom of the log right here. Okay. Now the inside of the log is the answer of the exponential, which makes it the value 16. And the power we have here is the answer of the log itself. So it equals -2. So far so good? So we just converted between exponential form and log form, back and forth. But let me make sure you guys have a clear copy of what I just wrote. So this is just me giving you a chance to copy this in case you couldn't. I'm just going to pause for a few seconds, so just pause the video and write this down if you want. Okay. Here's the second half of that. Okay. Now let's move on. Alright. Now, let's learn how to evaluate the logarithmic functions. Okay? So, this is number 8 in the notes, if you're following along on the notes with me. Okay, so we have log of 144 base 12. What does it equal? Yeah? Now, you can obviously use your calculator, but I would rather you do not. Not for these anyway, because it's good practice to try and solve them, especially since the numbers I'm giving you are going to give you integer x values. So, this is supposed to equal x because you don't know what the answer is, right? I'm asking you for the answer. So I'm setting it equal to x, and we're going to find what x is. Okay? Now the easiest way to handle this would be to convert this to exponential form, because exponential form is actually a lot easier to detect than log form, because log form tend to be a little confusing when you're trying to solve it. So let's convert this to exponential form. Base of the log is going to be the base of the exponential function, right? The answer of the log is the power of the exponential function. And what's inside the log is the answer of the exponential function, right? So there, we converted it. So 12 to x power, we don't know what x is yet, gives you 144. So what do you multiply 12 with to give you 144? Itself, right? Since it's a power, obviously. That was a trick question. Okay? So how many times are you going to multiply 12 by itself to get 144? And that's the easy part. It's 2. So x is 2. When you multiply 12 by itself, you get 144. Multiplication table, right? Easy. Okay, let me give you another example. Here we go. How about log base 64? So the base is 64 of 8. That's the number inside the log. Okay? So log base 64 of 8. And it equals question mark. We don't know the answer. I want you to tell me what the log equals. So I'm setting this to equal x. Okay. Now let's convert this to exponential form. Base of the log is the base of the exponential function. So 64. The answer is the power. So power of x. And what's inside the log is the answer of the exponential. Okay. Now let's think about this a little bit. The base is the number you're multiplying by itself, right? Because x is a power. That means we're multiplying 64 by 64, just x times. Okay? Now, what number would you place for x here for 64 to get smaller? Now remember, when we graphed exponential functions, whenever the power was negative, the entire thing turned into a fraction. So what would turn this value smaller is when the power is a fraction. So, for example, 64 is 8 squared, correct? So, what power would I use to turn it to 8 to the first power? Right? I'm trying to find the x that would turn this to just 8. Isn't that the same as taking the root? Right? Cancel, cancel. 8. So, what is x? When you take a root of something squared, what is the power of that root? What is it? X is 1/2. Okay? So this is the same idea as taking the root. Alright. Let me give you another example. I'm hoping that if I give you as many examples as I can, the idea would be a little clearer, because I know it can be confusing when you're not used to it, but I'm afraid the only solution for that is practice. And then you'll be able to spot the patterns faster. Alright? Okay, so in this example we have log base 3 of 27. Sorry, 1 over 27. So this is what's inside the log, and this is the base. Okay? And it equals something we don't know. We need to find what that is. So I'm calling that x. Now, first step, convert it to exponential function. So base of the log is the base of the function. So it's 3 to the power of x, and it equals the inside, which is 1 over 27. Now this is actually something we've seen the very first function we graphed in the previous video, right? So Whenever the answer is in the bottom, you know x is going to be negative. So I know x is a negative number. Now, what is that number? What gives you 27? 3 times 3 is 9, times another 3 is 27. So it's 3. X equals negative 3. Okay? Now, let me give you a few notes. This is what we call a common logarithmic function. So whenever you have log base 10 of x, okay? So if I give you a function where the logarithm is base 10, this is written as log of x, just like that. You don't write the 10. Make sense? So if I'm giving you a log that has a base that is different than 10, I will always write it down. Always. If you don't see a base, if you just see the word log and then what follows is the inside of the log, that means that log is base 10. No base is base 10. Okay? Another one is called the natural log. So the natural log is a log base e. You seeing this? So the number e we played with in the previous section is the base of this log. So whenever you have a log that has the e as its base, it's written like this, ln of x. So whenever you say this, ln, I'm talking about the natural log. The log of this base is e. Alright? Log of no base is log base 10. When you see ln, that's log base e. Alright? Now, let's do a few examples to practice. Here we go. So we have log of 100. What does that equal? X, right? Let's convert to exponential form. Okay, so we have the base, which is what? What's my base here? It's 10, right? Since there's no number written, it's going to be 10. To the power of x equals 100. How many times do you multiply 10 by itself to get 100? Easy answer. It's 2, right? Count the zeros. X is 2. Okay. How about this one? Log 0.0001. Answer is, I'll give you a second to figure this one out. Use your calculator, I don't mind. If you grab your calculator, here, let's do it. I'll do it for you. If you grab your calculator, this is actually a good idea. Let's practice writing the log on the calculator. So on your calculator, these are the two buttons you're gonna need the most. Actually, these three. These three right here. Okay? So this one, which is the one that most calculators have, is the normal log button. When you click this, you're gonna see just log of. Yeah? So 0.0004 close, find the answer, is going to be whatever this is. Oh, I have it on digital, hold on. Because I'm like, that doesn't look right. Shift. Okay, there we go. Need to be radius. Oh, I placed 4, not 1. That's why. Okay. Okay. So the answer is -4. Okay? Now, that means that the power of the exponential function was -4. So if I'm going to convert this to exponential, the base is 10. So base 10, power of -4, and it gives you 0.0001, which is true. Because if I'm multiplying 10 by itself 4 times, forget the negative for a minute, by itself 4 times. That's going to give you 10,000, right? 1, 2, 3, 4. Correct? That's 10 to the 4th. Now, since it's negative, that means it has to be on the bottom. So, that's what that equals. Now, if you want to write this in decimal form, it's going to look like this. Make sense? So the answer is negative 4. Like I said, use a calculator. Now I just want you to practice trying to find them out without the calculator in case you forget yours, or you're running out of time, or you just do it wrong on the calculator. Like, you need to be able to tell what it should be just by solving it out. You can always use your calculator, but let that be your backup plan and not your main tool, okay? But for these examples, let's just practice the calculator because I want you guys to get familiar with it. Most of you haven't been using this one. So let me give you another example. How about this one? Natural log of e to the 3rd power. Okay? Where's that one equal? Let's plug it in. Here you go. So we're going to use natural log. The button next to the log, right here. ln. See that? That's the one we need. So ln of e. So the inside itself is e. Oh, no, I tapped pi. Alpha. There you go. Now, this e has the power of negative 3. Boom. Yeah? So natural log has e to the power of negative 3. Which equals negative 3. So what happened here? How is the natural log? It just equals negative 3. Isn't the natural log base e? And we just plugged in e into it. So this basically means that the natural log, when you convert this to exponential form, natural log base e, so it's e to the base of the power, which we just figured out is negative 3, right, equals e to the negative 3. So I'm basically saying that e to the negative 3 equals e to the negative 3. Yeah? This is going to make a little bit more sense once I explain the inverses. But keep in the back of your mind, exponential functions and logarithmic functions are inverses either. That means if you have a log to a certain base, just like this example, for example, natural log base e, and you plug in the exponential equivalent of what that log is supposed to be. So in this one, it was supposed to be e to the negative 3rd. And I plugged in e to the negative 3rd inside. The log and the exponential are going to cancel, and you're going to end up with the power. But I'm going to explain that later. Okay? Now, let me give you guys... Oops, actually, I used the back of the page. So let me go back to the next one. Let me give you guys the properties we need before we move on. Okay, so here are basic properties. Please write these down before I continue. Here you go. First one. When you have a log base b of 1, it always equals 0. Okay? So if the inside of the log is 1, no matter the base, notice I wrote b because I don't care what it is. No matter the base, the result is always going to be 1. Because when you have that base to the power of 0, the answer is always going to be 1. So the result of the log is going to be the power used, which is 0. So log of 1 always equals 0. Log of 1 always equals 0. Okay? Number 2. Log base b of b So the inside of the log is the same as the base. The answer is going to be 1. Now, this can be further explained if I show you the exponential equivalent. So the base, b, power, is 1 and t equals b. For example, 3 to the first power is 3, right? So this is basically what that means. So whenever you have a base that matches the inside of the log, for example, log base 8 of 8, the answer is going to be 1. Because when you're trying to find the log, the answer is the power of the exponential function, right? So I'm basically telling you, when the base is 8, what power do I need to get the inside of the log, which is 8? So if the base matches the inside of the log, the answer of that log is always going to be 1. Always. Here's one more property. Log base b of b to the x power. Okay? Now this is just like the example I just showed you guys. So if the log has the exact same base as the exponential function you place inside, these two bases match, then the answer is just going to be x, the power of that exponential. For example, natural log of e to the negative 3. Natural log is log base e, and e to the negative 3 obviously has the base e. So they canceled, and the answer was the negative 3. Okay? Now, the reason for this is explained in inverse functions, the section we discussed before, where the domain and range of functions switch. Do you remember how we proved that exponential, a function and another one are inverses? We said that if you compose the two, the answer should be x. Do you remember that part? So if you have f of f inverse, so you place one inside the other, and if the answer is x, then these two are inverses. Well, here we go. The exponential placed inside the log, the answer is what? The answer is x. They're going to cancel. The log and the base cancel each other out, and you end up with the power, whatever the power was. Make sense? And last but not least, the opposite, because since this is true, this can also be true. Right? If you place f of x inside the inverse function, the answer should still be x. So, the opposite of this is also true. If I take the base, b, and place the log of that same base as a power, they're going to cancel. And you're going to end up with whatever the inside of the log was, which is x. Okay? So, if you have the exponential function inside the log, both the same bases, they cancel, and you end up with the power of the exponential as the answer. If you grab a log that has the base b and raise the whole thing as a power to a base b, the log and the base cancel, and you end up with whatever's inside the log, also the x. Make sense? So log base cancel each other, base log cancel each other. Alright, now let's do a few examples. Let me do this real quick so you can copy these. These are very important, you guys. Make sure you have these. Okay. Let's move on. Now, here's your first example. Log base 19 of 19. Looking at the properties I just gave you, what's the answer? Quick. The answer is 1. Base and answer match, right? Okay. Another one. Log base 10. What's the answer? The base over here is 10, so that means that the inside and the base both match, and the answer is also 1. Okay. We're using the properties for these examples for all of them, so you don't need to do a lot of thinking here. How about natural log of e? Base of this log matches the inside, so the answer is also 1. Okay? How about this? Log log of 273. This is your base. Now what's inside the log is 1. Equals what? 0. Log of 1 always equals 0 no matter what your base is. Case in point, I gave you a ridiculous one, 273. Where's that? Right? But it doesn't matter because any number, example, 273, risen to the power of 0 will always give you 1. Okay? So, no matter the base, if you take a log of 1, the answer is always going to be 0. Okay, another one. Log base 1/8 of 1 equals 0. One more. Log base 30, right, of 30 to the 10th power. So what about this one? I have the base 30, and inside the log I have an exponential, base 30, and I give the answer already, it's the power of 10, so it's not x, it's just 10. So what happens here? You have a log and a base, an exponential that has a matching base. These are going to cancel, and you're going to end up with whatever the power of the exponential was, which is the 10. Make sense? Okay, let's do another example. Man, I wish you guys were here so I could know if you guys understand this or not. This is a lot easier to do when you're in the room with me. So like I always tell you guys, just pause the video, look at the timestamp of what I was saying when you didn't get it, and email me and I'll explain it a little to you, okay? I don't care how many emails you send. Although if you do have more than one question, maybe you should put them in one email. But yeah, I don't mind as many emails as you need. And maybe I'll do another video to explain a little more. But anyway, so I'm hoping that if I do a lot of examples, this helps you guys catch the just patterns. Alright, one more example. Here you go. How about natural log of e to the power of -12. So natural log is a log base e, right? And I have e in the inside. So that is a log with a base and an exponential that matches that base. They're going to cancel, and the answer is going to be the power of the exponential. So it's -12. Again, I know because I'm using the properties. Just now I use this one. Okay. Now, what about let me see, something interesting. Ooh, let's flip it. You have 10 to the power of log of 14 equals what? Now notice, I gave you a log with no base. That means that this log has a base of 10. And this log happens to be the power of a base 10. So the base of the exponential is 10. The base of the log is 10. So these are going to cancel each other, and what's inside the log is going to end up being your answer. So the 14. Let's do one more. How about 8 to a log base 8 of 5. So log base 8, exponential base 8, they're going to cancel, and you end up the 5. Okay? Now, let me move this page real quick and show you what an exponential function looks like when you graph it. Yeah? Let's graph one. Now, if I give you y equals log of x, and the log has a base 3. Okay? So the log has a base 3, and we have x as the inside of the log. So to graph it, the easiest way would be to simply convert this to exponential form. So it will be the base 3, the answer, which is y, as the power, and the inside of the log as your answer. So this is what we're going to graph now. This is my function. So in this one, as you can see, the variable we're going to keep changing is y, and the result is going to be the x. Make sense? So when I do the table, x, f of x, which is y, right? I'm going to choose the numbers here. So 0, 1, 2, 3, -1, -2, -3. Plug them into the new function and find the x values, and that way we'll graph it. It would be a lot easier for you to do it that way than to try and plug in every single log value to answer it that way. Now you can, technically, you can create a table for this and plug in x values and find the y for each one. It's just that this is easier and can be done by hand instead of needing to use the calculator the entire time. So let's do that instead. Okay? So let's try. Here you go. Plugging in 0 in here. That makes it 3 to the 0, right? Which is 1. Anything to the 0 power is always going to be 1. Now, how about 3 to the first power? It's going to be 3. 3 to the second power is going to be 9. 3 to the third is 27. Now, when it comes to the negative, the answers are going to match these. They're just going to be in the denominator, right? So 3 to the -1 is 1 over 3. So 3 is just in the denominator. 3 to the -2, 1 over 9. Just like the 2 over here. It was 9, just in the denominator. And 3 to the -3 is going to be 1 over 27. So these are my points. Let's try and graph it. Here you go. 0 for y, 1 for x. 1 for y, 1, 2, 3 for x. 2 for y, this one, 9 for x. So I'm going to put it all the way over here. Oops, actually a little bit up, not that one. Hoping that turns into a 9. Right? Now, 27, I don't think I can graph that. So let's go to -1. So -1 for y, so I'm going down, is 1/3 for x. So right about here. Okay? -2, which is right here, is going to be 1/9. So getting closer to the y-axis. Yeah? Oh, it's actually on this side, sorry. There. And -3, you're getting even closer because it's 1 over 27. So the function looks a little like this. And it's getting closer and closer and closer, but never actually touching it. Going to infinity in that direction, going to infinity in this direction. This is your log function. Alright? Now, I want to show you guys a quick graph that compares both the exponential and the logarithmic functions. So say you have at y1 x0 function that goes like this and does this. This would be your exponential function. y equals b to the x. Okay? And we'll have at y0 x is 1, a function that does this. Yeah? And this is y equals log base b of x. This is a comparison between a logarithmic function and an exponential function and what the graphs look like. Now, let's compare. We'll do this real quick. I just want you guys to see what the domain, range, and other information about these two functions look like. So log base b of x. Right? Okay. Let's start with the domain. The domain of the exponential one is infinity, infinity, negative infinity to negative infinity, right? So as far as x is concerned, it's going to negative infinity and positive infinity. So negative infinity to positive infinity. Done. How about the range? So as far as the positives are concerned, it's going to positive infinity. So we know that. But it's never going to go to the negative. It's going to keep approaching 0, but never actually touches that 0. So it's 0, open-ended, all the way to positive infinity. Alright? Y-intercept would be the point 0, 1. This is the point it passes through. It has a y-intercept for the exponential functions. Also, you can technically have a horizontal asymptote at the x-axis because it will never touch 0. So you can say it has a horizontal asymptote at y equals 0. Okay? Now let's look at the log function and what properties it has. So, domain, as far as x is concerned, is going to both negative x and positive x, right? But wait, this is where x starts. Positive covered. For the negative, it seems to be getting to 0 but never actually passing it. So unlike the exponential one, this one starts at 0 and goes all the way to the positive. Yeah? Okay. What about the range? Now, for the range, so I'm looking at the y-axis. Negative, going there. Positive, also going there. So it's from negative infinity all the way to positive infinity. There. Right? Please notice. Domain of one is the range of the other. And the range of the first is the domain of the second. Domain and range were switched for the second function. Isn't that one of the characteristics we talked about when we explained inverse functions? Do you guys remember the group of the superheroes? And how one function can't have more than one x value that goes to more than one y value? And how I said that when you find the inverse, domain of one turns into the range of the other. So here we are. That just proves it. Exponential functions and logarithmic functions are inverse functions. Now, what point would this one pass? It's probably going to be an x-intercept because it's passing the x-axis, right? So while this one had a y-intercept, this one has an x-intercept, which is the point 1, 0. Which isn't surprising because, like we said, domain and range of the one function are going to be switched. So the point over here, you're basically going to flip the coordinates. So it was 0, 1, now it's 1, 0. Makes sense? And the vertical asymptote, which was the y equals 0, so the x-axis, turns into a vertical asymptote at the value of x equals 0, which is right here. Because this function is never going to cross the y-axis. It's never going to cross the value of x equals 0. So please write this one down. This is just an analysis to show you the relationship between exponential functions and logarithmic functions. Yeah. Now in the notes we have a couple of examples, but I want you guys to do these on your own and see if you have any questions for me, because I don't want to make the video too long. And the next one I'm going to play with the properties of logs, and we'll go into a little bit more practice on log and exponential functions. But this is basically the concept of both exponential and logarithmic functions. And I hope this video helped you guys get it. Let me know if you have any questions, yeah? Stay safe.